Forgetting about toes, men and women all have 10 fingers. So counting probably came very naturally to our prehistoric ancestors. Of course, human needs do not stop at the number 10 or even 20. One has to keep track of higher numbers. The rhythms of the human body have to be noted. Counting implies answering the questions, how many, how often? Counting is the basis of the idea of amount or quantity. One cannot rely here on memory alone. A permanent record is needed, and with time, such a record becomes required. This need to count, to tally and to record, increases as man's sphere of interest widens. The marking of days develops into the marking of the moon phases or months, and then into years. Other objects of interest also enter the story, such as lists of prime numbers. Some 4,000 years back, mathematicians in Babylon developed a system based on the number 60. We still use their measurement of time, with 60 seconds to the minute and 60 minutes to the hour. All our speeds and accelerations are dependent on this time scale. Furthermore, the Babylonians allotted 90 degrees to the right angle, and this remains in use today. As may be observed, the Babylonians possessed enough mathematical knowledge for daily use, including the surveying and mensuration of land. They could also approximately square the circle and solve equations. Books of concordance related to the Bible indicate that the word Babylon, referring to the city-state that became an empire, occurs no less than 250 times in the Bible. The ancient Egyptians used figures of different objects for syllables, sounds, words, and even numbers. These figures, or pictorial symbols, are called hieroglyphs. From the example given here, it may be observed that the ancient Egyptian manner of multiplication is just suitable successive addition. Check out the result for pi by assuming a circle with a radius of, say, 1 foot and using 8/9 the diameter. Wouldn't you say that this is pretty good for a few thousand years back? Situated just across the Mediterranean Sea from Egypt, ancient Greece was familiar with Egyptian mathematics. An important problem in Greek mathematics was the evaluation of cube roots of numbers. Square roots were easy. Another classical problem was the trisection of an arbitrary angle. Working with such insoluble problems enabled other important mathematical discoveries to be made. An etymological dictionary of the English language will clearly show that a large proportion of complicated words in English have a Greek origin, though many such words were imported into English via Latin. Ancient Greek was a highly developed language. The ancient Greeks produced many famous mathematicians. The entrance to Plato's academy had the motto, "Let no one untrained in geometry enter." The next few slides summarize the axioms and the geometrical postulates of Euclid. Euclid was a Greek mathematician who flourished in Alexandria in Egypt around 2300 years ago, and he is known as the father of geometry. Euclidean geometry is still studied in schools today. Perhaps it is useful to point out here that Euclid's geometrical postulates generally assume a two-dimensional plane surface without any curvature. The statement given in the present slide is Euclid's famous postulate on parallel lines. This postulate is often expressed in the form parallel lines meet at infinity. It is easily observed, even at a first glance, that the Roman numeral system is very cumbersome for all mathematical work. Roman numerals are really important only from the historical viewpoint. It can be claimed that mathematics did not develop in the Roman Empire as much as it might have done, because the system of numbers was basically unsuitable. Knowledge is not the monopoly of any country or any group of people. The discoveries of mathematics in ancient times were made independently by men of learning who had no contact with each other. The square root of 2 was a particularly important quantity because that was the length of the diagonal in a square of side equal to 1. Even a casual examination of history will reveal that reading, writing, and arithmetic, the so-called 3 R's, developed not in a rural but in an urban environment. The oldest known civilization in South Asia is that called the Indus Valley Civilization. On the map showing part of present-day Pakistan and India, the locations of Mohenjo-daro and Harappa are shown. Geographically, both these centers are close to the main system of large rivers in the area. The earliest basis for measurement is the human body itself. Feet and yards correspond to the human foot and its stride when walking. As may be observed, the Indus Valley people had overall a sophisticated system of weights and measures. Accurate measurement of heights, widths, and thicknesses is of great importance in the construction of buildings, both from the viewpoints of structural strength as well as appearance. Jainism is an ancient non-violent religion developed in India over the centuries. It lays stress on the purification of the human soul, and it encourages study and contemplation. The Jain contribution to mathematics is very significant, as may be observed in this slide. There is a Jain community of about 6 million people in India even today. We have now more or less entered the eras of recorded history. The development of mathematics began to be conducted in India in academic institutions. The study of astronomy was considered especially important because in India, in bygone centuries, eclipses portended bad luck and even disaster. Building on earlier mathematical work, the next step in South Asia involved the evolution of negative numbers, and inevitably this led to the concept of zero. At the time, it is observed that Indian mathematicians led the field. The progress of mathematical development in later centuries continued unabated in India, with major centers producing much academic work. One drawback of the system then was that only theoretical work was encouraged, and the applications of mathematics were downplayed. To sum up this survey of Indian and South Asian mathematics, it has to be said that work of great originality was produced in large quantities. Formulas that were later to be rediscovered in Europe during the Renaissance were developed. However, the thrust of the work did not improve the daily lives of the community in South Asia. China, called Zhongguo, or the Middle Kingdom in Chinese, is unique in having a history of virtually unbroken continuity over 5,000 years. However, there appears to be some shortage of documentation relating to mathematics in antiquity. As in other old civilizations, such as India or Egypt, mathematics and astronomy are intimately related in the early development of mathematics in China. It should be added that in ancient times, the relative positions of planets and stars in the night sky were also assumed to have an effect on human fortunes. Astrology provided a fertile area of study for such non-scientific activities. This book, called The 9 Chapters, is more or less a compendium of Chinese mathematics from the earliest times, and it served as the main book of reference for mathematicians in China for many centuries. The book was translated into English 120 years ago. A Chinese mathematician ahead of his time was Liu Hui. His painstaking calculations for the value of pi, as well as his geometrical applications of a theorem similar to Pythagoras' theorem, are especially noteworthy. From the Chinese numerals, it may be observed that no other system approaches the flexibility and the facility of the currently employed universal Arabic numerals. One of the major disadvantages of all other systems is the lack of a suitable symbol for zero. The additive property is simple, but numbers are not positional in the Chinese system. Hence, representing Chinese numbers is easy, but all arithmetical operations become difficult. The next few slides indicate the development of Chinese mathematics from the 5th century onwards. There is a long progression of qualified mathematicians covering the same ground as their counterparts in other countries. Because of the long, though often impassable, border between China and India, there was a certain amount of borrowing from Indian mathematics by the Chinese. The Chinese adopted mathematics as a subject for the civil service examinations in the 6th century. This gave mathematics both importance and prestige. It also contributed to the development of Chinese mathematics. The preceding slides indicate the vast progress made by Chinese mathematics over many centuries. It is not necessary to memorize the names of the mathematicians involved, but to note that great progress was made during these centuries in Chinese mathematics. The Mayan system of numbers is additive, which resembles the Chinese system. It does have a symbol for zero and also has positional properties, but on the whole it is a complicated system. The Mayans were a developed civilization, but not enough information is available on their mathematical achievements. Mayan documents were destroyed by invading Europeans. The ancient Egyptians did have a concept of nothing. Nothing was where you started from, and if you took 2 apples away from a basket with 2 apples in it, you were left with nothing. But they never considered that nothing might be represented by any numerical symbol. As with the ancient Egyptians, so with the ancient Greeks, nothing remained just an idea and was never crystallized into a numerical symbol. Once the symbol for zero began to be used, there was no looking back. There was finally something which could be used to represent nothing. However, by this time, many centuries had elapsed since the ancient Greeks and Romans and Egyptians. Furthermore, in those days, when travel was on horseback, it took ages for knowledge to circulate. The symbol for zero thus took some years to spread. Leonardo Fibonacci lived roughly from 1170 AD to 1250 AD, and he was a very talented mathematician from the Italian city of Pisa. He was also famous for his discoveries in number theory, especially the Fibonacci numbers that give the golden ratio of 1 to 1.618. In the next few slides, the intention is to have a closer look at some numbers. After all, numbers are the bread and butter of mathematics. Of a brilliant Indian mathematician called Ramanujan, who died at the age of 32 in 1920 and produced great results in number theory, Professor Littlewood of Cambridge has said, "Every positive integer is one of Ramanujan's personal friends." Over the years, the properties of the number 1 have excited the curiosity of many major mathematicians. As may be observed from this slide, much work has been done on the matters relating to the number 1. As may be observed from this verse, a reasonable value of 3 is obtained for pi by dividing the circumference of the circle by its diameter. The biblical reference to the circumference and diameter indicates that interest in the value of pi goes back thousands of years in the Holy Land, which is now situated in the Middle East. Many practical attempts have been made to derive or devise close approximations to the real value of pi. One of the approximations proposed by Archimedes, that pi may be taken as 22/7, is often used even today. Zhu Chongzhi of China proposed the value 355 divided by 113 for pi about 1500 years ago. This gives a very accurate result for pi. Today, of course, pi is available on every little desk calculator, but in times gone by, students had to memorize it to several places after the decimal point. As you may observe from this slide, they had to memorize pi in France as well, as a number useful to wise people. The transcendental number e, which equals 2.71828 when taken to 5 places after the decimal point, is intimately connected with logarithms. E stands for exponential, referring to raising a number to a certain power. The calculation for the area under the rectangular hyperbola xy equals 1 is illustrated in these 2 slides. From the integral, it is observed that the area under the hyperbola xy equals 1 between the limits of 1 and e is a unit area, or 1. Some decades after Napier, Jacob Bernoulli found out that the number e was the basis of compound interest calculations. $1 at an annual simple interest of 100% will, after 1 year, become $2. However, if compounded continuously, $1 will become E dollars, or $2.718 at the end of 1 year. These 2 slides illustrate this result. This slide shows a graph of y equals e to the power x, where x is time and y is the resultant population. Leonhard Euler, in the 18th century, produced an infinite series for E. Euler was a Swiss mathematician who wrote very many books. Although not used as often as pi or E, the imaginary number I opens up a whole new area of mathematical manipulation because of the equation I squared equals -1. Complex numbers have both real and imaginary components. Such numbers are usually represented on a set of coordinate axes, where the x-axis depicts the real part and the y-axis the imaginary part of the number. Calculus is a branch of mathematics that deals with the variation of one quantity relative to another, whether it is velocity with respect to time, or slope with respect to distance, and so on. We may recall from high school mathematics that the derivative of a function gives us a kind of slope, and the integral of a function gives us a kind of area. Because calculus deals with continually changing variables, the value of the derivative, as also the integral, changes from point to point, and its value at a given location is obtained by making a variable tend to that location. This is called the value in the limit. The physical world has to be interpreted in terms of ever-changing quantities and the relations between these quantities. Calculus, which makes this possible, was developed in the 17th century independently by Isaac Newton in England and Gottfried Wilhelm von Leibniz in Germany. As will be observed from lectures in the other STEM disciplines, Newton, in his long life, was responsible for so many scientific discoveries that this statue of Newton in Trinity College, Cambridge, bears the inscription, "Who surpassed all men in genius." The applications of calculus are legion. From the motions of particles to the motions of planets, from wave propagation to radiation, all physical phenomena need calculus for their investigation. Every graph that we have ever drawn is actually a tribute to René Descartes. Descartes showed that every equation can be pictorially represented on a set of rectangular coordinate axes. Here we have the equations for some common two-dimensional curves. Try plotting them on graph paper to a suitable scale to check their shapes. Choose suitable values for the constants. We have had occasion to mention Leonhard Euler earlier in this presentation, and his name will crop up again and again because of his great contributions to mathematics. Euler had an interesting and very productive life. Civil engineers particularly revere Euler because they use his formulas for investigating the stability of columns in buildings. Engineering has practical applications, but all practical applications have to be backed up by theoretical analysis. The three countries where Euler worked, Germany, Switzerland, and Russia, have all produced commemorative stamps honoring Leonhard Euler. Euler is responsible for deriving the strange equation that brings together two transcendental quantities, E and pi, an imaginary number I, and the two special numbers 0 and 1. Inspiration can come in the most unlikely places to those who think. This humble bridge, Rmueom Bridge in Dublin, Ireland, was the place where Hamilton mentally finished a complex mathematical analysis. The formula quoted here is frequently used in vector algebra. What is remarkable is that it is one of the few solid commemorations of an important mathematical discovery. All sorts of claims have been made for the golden section or golden ratio of 1.618 or its reciprocal, which is 0.618. In any given hive, for example, it is said that the ratio of female to male bees is around 1.618. If you measure the distance from your shoulder to your fingertips and divide it by the distance from your elbow to your fingertips, you get around 1.618. Try it. In the next few slides, solved examples of simple daily mathematical problems will be presented. All students should be able to follow them without difficulty, as they are meant both to amuse as well as to instruct. The next two slides list names of great mathematicians of the last 3 centuries. Of course, the list is both compressed as well as selective. However, the lives of great mathematicians deserve to be studied. There is a spark of the divine in mathematics. Mathematics is perhaps the most challenging intellectual discipline, and to produce new work in mathematics is extremely demanding. Still, mathematics will always remain the most attractive research area for first-class brains.